All right, so today we're going to talk about quadratic transformations. And so now, not just shifting up and down and left and right, but now we're looking at A and B, and that's going to tell us whether we have this vertical stretch or shrink or this horizontal stretch or shrink. And so what we need to do is when we're looking at the letter A tells us our vertical stretches and shrinks. So vertical is going to be on the outside. So we do need to know that. So for A, your vertical is going to be on the outside of the function. The easiest way to remember that is that your inside is your horizontal. So your horizontal always occurs on the inside. So we have the word high, right? So horizontal will always be on the inside. And that's true for left and right and for the horizontal shrinking and stretching. In the same way, this vertical is true for the stretching and shrinking. But it's also true for the movement up and down. It's outside of the parentheses. So when I say inside and outside, think outside or inside of the parentheses. Now, letter A, just a quick thing real fast. If A is greater than 1, so if it's a number larger than 1, then we have what we call a vertical stretch. And then if you remember, it's by a factor of, so we say BFO, which is by a factor of whatever that value A is. So in this case, this is not a number greater than 1. So what happens here? So when A is some number in between 0 and 1, so think fraction. I just hesitate to say that because technically 4 over 3 is a fraction, but that fraction, 4 over 3, is technically greater than 1. But I'm never going to trick you like that. So when you see a fraction, a number in between 0 and 1, like 1/2, then what happens is it's vertical because it's on the outside of the function, outside of the parentheses, but this is called a shrink, a vertical shrink, and we still say by a factor of, you don't have to write that out every time, just BFO, by a factor of A. And so in this case, we have a vertical shrink, and this is by a factor of 1/2 because A is 1/2. That's going to kind of act as our slope from our vertex to our next point. So do you see how when A is typically 1 in our parent function, our slope is up 1, right 1. And because it's symmetrical, it would also be up 1, left 1. Very similar to absolute value, except that slope analogy kind of breaks down when you try to find other points. But again, you can use your graphing calculator to help you out with that. Now remember, on the inside of the function, we're saying the opposite of h. So the opposite of a -2 would be that +2. So that means this is going to go to the right a distance of 2. So this goes to the right 2. And then we have +4, and so that's on the outside of the function. So that means we're going to go up a distance of 4. And so we want to say, hey, we're going to go up 4. I do want you to write these 3 steps down. I want you to write all the steps that you have. And then now we just have to translate that over here. So we're going to go right 2, up 4. So starting from our vertex in purple, my f of x, we're going to go right 2, up 4. So 1, 2, 3, 4, boom. My new vertex is at that spot. Now I need to find other points. Well, what is my slope? We have this vertical shrink by a factor of 1/2. What does that really mean? So think of it as slope. To find this next point, I'm going to go up 1, right 2, so about right here, and up 1, left 2, so right here. And notice how we have this kind of wider function. So this is, in purple, this is f of x. And it makes sense that it's wider because this is a vertical shrink. So remember vertical, think of like testing your vertical leap, your vertical jump. That's how high you can jump, so think vertical up and down. If I'm shrinking it and I had this huge lump of Play-Doh and I pressed down, I'm shrinking it vertically from top and bottom, where's that Play-Doh going to go? Well, it's going to come out. It's going to be wider. And so in the same way, if I took this graph in black and I pressed down, it's going to become wider. And notice how it is. It's getting wider. So it is being vertically shrunk by a factor of 1/2. Number 2, in the blue, we have no shifting or translating from left to right. So there's no +5 or -2 or anything like that. But on the outside, we have this -2, and this means we go down 2. So we are going to go down 2 from our vertex. So our vertex is now going to be here in blue, and this is for g of x. So this is our function g of x. Now, this 3, again, is slope. So really, whether it's on the inside or outside of the parenthesis, it's basically slope. So this is 3 over 1, technically. And so 3 over 1, we're just going to go up 3. 1, 2, 3. Right 1, boom. And because it's symmetrical, we're going to go up 3, left 1. Boom. And so this looks like a vertical stretch, doesn't it? It looks like we took this and we vertically stretched that to make it skinnier. But it isn't vertical because it's on the inside of the function. And so remember, horizontal occurs when it's on the inside. So when we see a letter B, a number attached to x, on the inside of the parentheses, this is letter B. We have some more notes that we need to know. So for example, when B is greater than 1, it's backwards. It's now a horizontal shrink. So this is a horizontal shrink, and we would say by a factor of 1 over b. So you take the reciprocal of that. Also, it's opposite here. When b is in between 0 and 1, so when b is a fraction, we have what's called a horizontal stretch. And then we still say by a factor of 1 over b. So the horizontal gives people the most challenge because not only is it opposite of the vertical stretches and shrinks in terms of when they occur, but also it's not just by a factor of the number there, but it's by a factor of that reciprocal. So for example, 3 is a number greater than 1. So here we have this horizontal shrink. So not only are we going down 2, but we also have this horizontal shrink. And we would say by a factor of 1 over b. Well, 3 is b, so 1 over 3 is 1/3, right? 1 over 3. Now, what's interesting with this is that a vertical stretch and a horizontal shrink, if I press in from left and right and I'm shrinking this and I had a lump of Play-Doh, where's that Play-Doh going to go? The only way it can go is up and down. So a vertical stretch and a horizontal shrink look the same on a graph. Just like a vertical shrink or a horizontal stretch look the same on the graph. So that's why if you looked at that and said, oh, hey, that's a vertical stretch, you're kind of right. But because of the function that we're given, we have to say that it's a horizontal shrink. So it's a skinnier graph than its parent function. All right, there's one more thing that we need to know, and that is what happens when a is negative. What happens when we have a negative number out in front? So you probably already know this, but when a is negative, or when a is less than 0, which is negative numbers, we have a reflection about the x-axis. So this reflects the x-axis. Now, if you want to say it just flips down, that's fine. So instead of our U-shaped graph opening up for all of these, because a was a positive number, anytime a is a negative number, everything's the same except for now it opens down, it flips down. Let's see what that looks like here. So because of this negative, we're going to open down or reflect over the x-axis, or it's going to become an N-shaped graph. Okay. Because of this positive 3 here, this positive 3 means we're going to go up a distance of 3 because it's on the outside of our parentheses and it's separated by that plus or minus, so we're going to go up 3. And then this 2, we're ignoring the negative now, but this 2, that is a because it's on the outside of our function and it's attached to our x squared. So because it's on the outside of the parentheses, we don't have parentheses, so you assume outside. A is 2, well 2 is a number greater than 1. So this is a vertical stretch, so because of this 2, this is a vertical stretch. We would say by a factor of whatever a is, which is 2. Now I realize a is a negative 2. Be careful of that. Technically the formula is that we take the absolute value of a. And so vertical stretch by a factor of 2. So do not put negative 2 there, because it's the absolute value of that negative 2, which takes all negatives and makes them positive. So vertical stretch by a factor of 2. Now, what does that look like? So we're going to open down. That'll be the very last thing we do. We're going to go up 3, and we have this kind of slope of this 2. So we're going to go up 3 from 0, 0. So up 3, and we're we're not going left and right, so there's this. And my slope again, think of that value as our slope. And because it opens down, we're going to go down to right one and down to left one because it's symmetrical. And so now we have this U-shaped graph, or this N-shaped graph, sorry. This U-shaped graph that was flipped over the x-axis, or reflected, or opens down. And now it looks like this. Now, it is skinnier than our original, so it makes sense that we have this vertical stretch. So even though it opens down, it is not as wide as our original function. So we have this vertical stretch by a factor of 2. So that number, a or b, that's attached to your variable, will kind of act as your slope from your vertex to your next point. And then remembering that these are symmetrical about what we're going to learn soon, that's called the axis of symmetry.